Okay. Check. Okay, so we're looking at a few of these. We're going to start with... well, we have time, so we might as well do one also. So we're going to do a little bit of skipping around. We are going to start with one. Just a little skipping around. So one, we have radius of convergence for the power series. The power series looks like this. n plus 1. This is unnecessarily complicated. Over 4 to the n. Times x minus pi to the n power. And we just want the radius. So number one, it's not geometric. Darn it. If you have trouble seeing that, then yes, you would write down the first 4 terms. But this one's pretty safely not geometric. We have an n that does not appear in the power. So let's write the first few terms. No, let's use a ratio test. So we want the limit as n approaches infinity. That's going to turn to n plus 1, n plus 2, n plus 3 over 4 times 4 to the n. I forgot about x minus pi. Times 4 to the n over a mess. n plus 1, n plus 2, x minus pi to the n. Force that to be less than 1 so we can locate our radius. Things cancel out nicely. Notice the n plus 1 cancels with the n plus 1, n plus 2 cancels with n plus 2, x minus pi, 4 to the n, 4 to the n. That's really nice. Okay, so the x minus pi over 4, that can't really do anything with that.
X minus 4.
And then we have n plus 3 over n. Force that to be less than 1. This limit here is 1. So we get absolute value of x minus pi over 4 is less than 1. And when you multiply both sides by 4, you get the absolute value of x minus pi is less than 4, giving us a center of pi and a radius of 4. And of course, the radius is what's being asked.
So I was asking for the interval from 4 to the pi minus 4 and pi plus 1 and test it.
And then test the endpoints, yeah. Yeah, go ahead.
So that's when you actually have to get the x by itself, right?
Yeah, if you're doing anything more than just the center or just the radius.
You guys have that.
Yeah. Luckily, we don't have to. Question 2, interval of convergence. Okay. So we have this series, the natural log of x to the n power, and it's if you didn't see that is a geometric series, you would write out the first few terms, or you should write out the first few terms. So remember, if you're using the ratio test, you have to or if you're using the ratio test for an interval, you have to use the check the endpoints. But since we're not, kind of done here, this is a geometric series. The center is, well, I don't know what the center is, but I know the radius, no, the ratio is equal to the natural log of x, which is a little different than the stuff we've been working on. That's not polynomial in nature anymore. So you have to treat it a little differently. So we know the absolute value of the natural log of x needs to be less than 1 for convergence because we have a geometric series. And then to solve that, you'll have to set up this inequality. And then you're going to exponentiate. And that gives you 1 over e is less than x is less than e. And that's my interval. One more time?
Okay, so because the absolute value of natural log of x is less than 1, so
Huh?
that's why you put negative 1 is less than natural log, which is like less than.
Yeah.
So you just have the inequality with the radius, right?
Yeah.
So like if that was 2, you'd make it from negative 2 to 2?
Yeah.
Okay. Because it's geometric, you don't test endpoints.
And because it's geometric, you don't have to test endpoints. Since the series is geometric, you don't need to test the endpoints. Note, if you use the ratio test for this problem, you will be marked down if you did not test the endpoints.
So then if it's geometric and you don't test the endpoints, you just assume you're right.
Yeah. Geometric never converges at the endpoints. So you don't have to test them. Okay, and number 3.
It's fair.
Mhm.
If it's a geometric but you did use the ratio test,
You still have to test the endpoints.
okay.
Anytime you use the ratio test, you have to test the endpoints, geometric or not. Which is why you don't want to use the ratio test for a geometric series. Alright, 3. Okay, we have x squared minus 4 over 21 to the n power. And if you don't see this as geometric, you do want to write out the first few terms. That's 1. What a weird series. I mean, why would you have 21? Under what circumstances would 21 ever be a denominator?
Yeah, 7 right there.
7 and a 3 in the numerator. Okay, so that clearly looks geometric. So we could just use the geometric center here. I don't know what the center is. This isn't polynomial in nature, right? Or it doesn't look like x minus center. So we'll just leave a question mark there. We're not sure. I think it's, no, I don't know.
If you have to write that, like just, you don't know the center, you just do the ratio.
You could just go to the ratio or the geometric test at this point.
Geometric ratio thing.
Yeah, but I'm putting it here just for reference.
That's about the radius or about the ratio?
Oh, you're right, ratio. Yeah. I have problems with that because both words start with R. It's confusing. Okay, so the ratio is x squared over 4. So the absolute value of the x squared minus 4 over 21 needs to be less than 1. Or the absolute value of x squared minus 4 needs to be less than 21. Okay, so this is going to be a little bit special because you have the square. Solve carefully because of square. And so what I mean by that is, just like you did for the natural log, do the exact same thing. Okay? Add 4 to both sides. Well, this is ridiculous right here, isn't it? Okay, the x squared is always greater than negative 17, right? So all this really says is x squared needs to be less than 25. Which means x needs to be less than 5. Interval of convergence. Negative 5 to 5. Okay. Like you said, we're skipping around, so we're going to skip to 8. And we're supposed to find interval of convergence for the series x minus 9 to the n. 6 plus 2n. This is non-geometric. So we'll use a ratio test.
Should we write that as an
Is it imaginary bonus point?
It's not certainly something that would give you points, but it kind of gives the person reading your test some insight into what you're doing. Okay, so the limit as n approaches infinity of x minus 9 to the n times x minus 9, 6 plus 2n plus 1, 6 plus 2n over x minus 9 to the n. Force that to be less than 1. Do some canceling. You get x minus 9 times the limit let's see, 6 plus 2n over 8 plus 2n. Now there are many ways to show it, but this limit here is 1. That goes to 1. And so the absolute value of x minus 9 is less than 1, giving me the open interval 8 to 10. And that ends phase 1 of our operations. Time to go to phase 2. We check endpoint convergence. Okay, when x equals 8, our series becomes negative 1 to the n times 1 over 6 plus 2n. This is an alternating series, so you're going to use an alternating series test. The limit as n approaches infinity of 1 over 6 plus 2n. What is that limit?
0.
Clearly 0. Therefore converges. What about when x equals 9? I did mean 10. I did mean 10, thank you. Your series becomes 1 over 6 plus 2n, which is not alternating, nor is it a p-series. So we're going to use LCT, because it's close to a p-series. Compare to 1 over n, which diverges. We do the limit as n approaches infinity of 1 over 6 plus 2n over 1 over n. That's equal to the limit as n approaches infinity of n over 6 plus 2n. There are many ways to do it. You can look at the lead term test. It's n over 2n. You can simplify the lead terms. That's 1/2. You can use L'Hopital's rule, 1 over 2. But either way you do it, you're going to get 1/2. So therefore, this series diverges.
Just to review, alternating series, if it's only if x if it equals 0,
Only if the limit of the general term is 0.
then it converges.
Mhm. Okay, so the interval of convergence, x must be in this interval closed 8 to open 10. And that's that. Huh?
It wouldn't have any sense to do the ratio test again to check for endpoints, right?
You could do the ratio test again if you wanted to.
So
You can, yeah.
How do you pick a power series to go, like, for the limit comparison, how would you pick one?
In this case, because it's a polynomial down here, we would, what I would do is, I would look only at the lead terms. Okay, so the lead term in the numerator is 1. The lead term on the denominator is 2n. Then if there are any numbers left, I would turn the numbers into a 1. Okay, any more suggestions? Should we do 9 for funsies?
Sure.
9 looks like it's going to be all real numbers to me. Did you catch that when you get an n factorial on the denominator?
Converges.
It's usually all real numbers
Do you have an n factorial?
on the denominator. That's not balanced out by the factorial in the numerator. Actually, that would never happen, yeah.
Is it always that way, or is it just...
I hesitate to say always because I bet someone's going to find the case where it
N to the n
isn't.
goes faster, right?
But I'm pretty sure. What was that?
N to the n goes
N to
faster.
the n goes faster. Yeah, so if you have n to the n over n factorial, you'd have problems. Okay, so let's do this. We got x minus 3 to the n over 3n factorial. Okay, the factorial makes it not geometric. So we utilize a ratio test. Limit as n approaches infinity. Let's see, this first one is x minus 3 to the n times x minus 3. And this is 3 n plus 1 factorial. Times 3n factorial over x minus 3 to the n power. Force that to be less than 1 if possible in this case. We get some canceling. We get x minus 3 there. Limit as n goes to infinity. That's 3n factorial over 3n plus 3 factorial. Force that to be less than 1. So annoying. I get some point it stops advancing by 1 line and starts going by 3 lines. I never know when that point is. X minus 3, multiply by the limit. That's 3n factorial. Denominator is 3n plus 3, 3n plus 2, 3n plus 1, 3n factorial. Okay. At this point, you should start noticing that this is not going to be less than, there's always going to be less than 1. These cancel out. You get the limit as as n approaches infinity of 1 over 3n plus 3, 3n plus 2, 3n plus 1. This limit is 0. So we get 0 is less than 1. Whenever you get 0 or a number less than 1, the conclusion is series converges for all real numbers.
What would be an example where it would be less than 1?
I can't think of one that doesn't go to 0.
Yeah.
I mean, all the x's would have to cancel out, and that's not likely to happen.
How did you break up the denominator, like 3n plus 3, 3n plus 2, 3n plus 1, and 3?
I need to do that so I can cancel out the 3n factorials.
Oh, okay.
Yeah. So I had to get 3n plus 3 factorial. I had to simplify that enough until it got to 3n factorial. Converges for all real numbers, or you could write converges for x element of the set of real numbers, or you could write negative infinity less than x less than infinity. All three of these would be marked the same. Let's do 10 and then be done with it. 10.
It's easy.
10 is geometric. (16 to the n). So whenever you see that n appearing only as a power, you need to be suspicious about this being a geometric series. So if you don't notice right away what the ratio is, write out the first few terms. So when n equals 0, you get 1. When n equals 1, you get x minus 6 squared over 16. When n equals 2, you get x minus 6 to the 4th power over 16 squared. When n equals 3, you get x minus 6 to the 6th power over 16 cubed plus dot dot dot. So hopefully seeing it like this makes you realize you have a geometric series. It certainly looks like the center is 6. And the ratio is x minus 6 squared over 16. So for your test, then the limit, no limit, the absolute value of x minus 6 squared over 16 needs to be less than 1, which says that the not even absolute value anymore. X minus 6 squared needs to be less than 16. The absolute value of x minus 6 needs to be less than 4. So the center is 6. Radius is 4. 6 minus 4 is 2. 6 plus 4 is 10. And then you're done.
test for 8 and not for 9?
You mean the endpoints?
Oh, yeah, yeah.
Yeah. 9, there are no endpoints because our radius is infinite. So you're not going to substitute infinity into the series. Okay?
I'm just wondering.
Yeah.
Why did wherever n diverge?
Yeah.
I'm just like thinking about that. Like after a long point, you just be adding 0 over and over again.
Yeah. I mean, how do you want to show it? You can show it with with an integral test. You can show it with a
This equals ln.
yeah. You can show it with an integral test. You can show it with a no, I think the ratio test is inconclusive. But I think the integral test definitely shows it. And you can also look in your calculator too. I mean, if you
But like
keep-
logically.
yeah, logically it seems like it should, but it doesn't.
It's,
Yeah. Didn't we call it the exception when we first started?
yeah.
Yeah.
So.
Okay, I'm gonna stop the recording and that's it.